Okay, so we are now doing related rates. Okay, so related rates is all about finally using in real-world application all the tools that you've been learning all this time, from geometry to pre-calc to everything all together in solving real-world problems. There's not just one way to do this, and that's another thing that makes it difficult, because your way might be different from someone else's way. But there is some sense of consistency amongst them that I will give you that template, and then from there you'll develop your own understanding. Here we go. So in the last section we learned to differentiate implicitly defined functions by using the chain rule. Remind me again, implicitly, what are we talking about? Derive first and then find dy dx later. Okay? And the thing is that there's multiple variables that you're deriving. Okay? So in this section we will use the chain rule to find the rates of change, i.e. slope, i.e. the derivative, of two or more variables. Well, we've kind of already done this, but this is new. So related in respect to time. So time, t for time if you will, that is the variable that we're taking it in respect to. So Lexi right now is changing. You can say dl dt. Kevin is changing right now. You can say dk dt. Luke is changing, dl dt. On a continual basis, you are always changing. So what we're doing is we're measuring these changes that occur at certain times. When I'm at a stoplight, things are changing around me. Whether it's cross traffic, whether it's traffic with me, if I'm moving, things are always in motion is what I want you to visualize, okay? All right, and all we're doing is taking snapshots of time. So the given expressions, dy dt, dx dt, dv dt, what do you think this v stands for? Velocity? Actually, it does not. Velocity normally is dy dt. What do you think dr stands for? No worries, I want you thinking. I want you thinking about these. And if you're getting them wrong, it's okay. We're going to talk about what it represents. Dr dt is the radius, like the radius of something. Okay? So dx dt is the rate of change of a horizontal in respect to time. Dy dt could be the rate of change of a vertical length in respect to time. Now that I've said that, what do you think dv probably stands for? The volume. So not only are we talking about one-dimensional things that are changing, we're talking about two- and three-dimensional models that are changing on a continual basis. So there's a lot going on. Okay, here we go. Let's start off with mechanics. Suppose we have, bless you, suppose we have this equation that's given with these two variables, and we're asked to find dy dt when x is 4. And the parts that we are given are dx dt is 2 and x is equal to 4. Okay, Spencer, what do I do first? What do you think we should do first? Sorry, what do you think we should do first? Yeah, just take the derivative. If in doubt, guys, for the first semester, that's what we should always do. Take the derivative, okay? So implicitly, anyone, it's different today. Because we're talking about time and change, okay? So what's the derivative of y in respect to time? Go ahead. Oh, no, sorry. We're just going to derive this equation right now. What's the derivative of y? What do I write down for the derivative of y? dy dt. So now we're changing. Dy dt, because no longer are we talking in respect to x, now we're talking about in respect to time. Physics-based problems. Okay? The derivative, Because remember, we're in respect to time, of 5x squared would be what? 10x dx dt. Because now we're saying, what's the rate of change of x? It's all implicit. It's all chain rule still. Okay? And then minus what? Yeah, minus 6 dx dt. Plus what? Plus 0. We good? So now all we're going to do is plug in the pieces that we're given. X is 4. Dx dt is 2. And that's it. So we'll say 10 times 4 times 2 minus 6 times 2. And this is going to give me what? 80 minus 12? 68. Now here's the thing. What you're going to learn a lot this year, this unit is 68 what? First of all, let's interpret this. Let's interpret this. Is this f prime, which is normally like a velocity of something, where f double prime is like an acceleration of something, or is it just f of x, which is a position of something? Which of these three is dy dt representing? Velocity. So what we're thinking about is a velocity or rate of change of y. And just a brief thing that I could show you is, let's say that I had a ladder that was leaning on a building, if you will, and I called this x because it's horizontal. I called this y because it's vertical, and I call this z because it's diagonal. This is a way of saying what's the rate of change of y in respect to time. You with me? So give us, especially those of you in physics, what kind of units per measure could I give to 68? Meters per second? Now look at all this small little subtle details that you have to interpret because of this word right here. Because this is a positive 68, what is this going to be doing? It's going to be moving up. It's going to get bigger and bigger and higher and higher and higher. So what's happening is this ladder per se, which I won't let me grab individually, is going to like a fire station would go out. It's just extending, and it's making that y representation increase.
So X staying?
Say again?
X staying?
X is staying the same for now. And that's the thing. Sometimes X will stay the same. Sometimes X will change at the same rate as Y, or proportionally to Y. So that's an awesome observation. What's constant and what's changing all in real time as this thing is happening. All right.
Wait. So what is that dx over dt equals to? What is that like represented?
What dx is, so this right here is saying this x for here, for this particular one. Now I know I gave it an example. Nice question. I know I gave it an example with the ladder. And if we did it with the ladder, I mean, it'd be a little bit different. We're going to do some of those today. But for right now, just keep it as just the numeric values for now. Okay, we're going to tie it to, I just wanted to get units in your brain for right now. Awesome question. So a pebble is dropped in a calm pond, causing ripples in the shape of concentric circles. So these concentric circles, they're just saying circles that are kind of outside of each other. Okay? So the radius of the outer ripple is increasing at a constant rate of 1 foot per second. Here we go. I gotta start you off immediately with the acronym. Now, I'm not even kidding. Because of the fact that this was such a dreadful unit, I'm not even kidding. We developed this like the very first year that I taught calc, and it helped a lot of students. acronym, because it's such a dreadful unit, DREADS is the acronym that I think you should use. That will at least get your brain going as far as what are the steps that I could start off at and where I should be looking and when I should be asking myself these questions. Because a lot is going on. And this is as close to a template that I could come up with. Number one, draw the diagram. If you see it, it's so much easier to start setting things up. And you don't have to go crazy and elaborate, just draw the diagram. Number two, rates that are given and the ones that we need to find. This is so important to get started off. What do you think E stands for? The equation. What equation are you working with? Are you talking about the equation of a circumference of a circle? Are you talking about the equation for the surface area of a triangular prism? What are you talking about? So the equation relates, otherwise related rates, it relates all the pieces together that you're trying to look at one specific point in time. What do you think the second one, or this D, represents? The derivative. This is the derivative, yeah. The differentiation of this equation. So the derivative of this guy. You with me? And guys, if you want to, please put it in your notes. Most likely it's going to be in implicit form. Okay? And then the last one, the last two are substitute the given information and solve for the unknown. If you do this, I guarantee you have a fighting chance. Like 90%, you're almost guaranteed that you will be able to do this. If you know the calculus steps, you'll be able to solve this problem.
You said the derivative will pretty much always be implicit.
Implicit, yeah.
Like in the example you gave us, there was the y on one side that wasn't obviously an implicit equation. When would it not?
It will. Just go for implicit. And here's the thing. I like his question and the timing because it makes me clarify just a little bit better. The more thing that I want you to gravitate to, it's going to be in respect to time. So all these small little variables are going to be in respect to time that you're deriving. Okay? And if it's explicitly given to you, that's okay as well. It could be both. But what I needed to clarify is it's in respect to time. Questions? Yeah?
So is it only explicit on time on that side by itself?
Or when any variables on them. But the thing is, we're going to have multiple variables. You'll see what I'm talking about when we get there, okay? All right. Diagram, done. The rates that are given. Well, this sentence right here gave us a rate. And the reason why I know it gave us a rate is because it said it right there. That important word will tell you you were just given something dt just now. Okay? So d something dt is equal to 1 feet per second. Now, can you tell me, the 1, the way it's given, it's positive. What's happening with these circles? They're growing. If it was a negative 1, what would be happening with the circles? They'd be decreasing. That's huge. You got to get that in your brain right now. If the rate of change is positive, then the function is increasing. Again, if f prime is positive, f of x is increasing. But if f prime is negative, f of x is decreasing. Okay? All right. So what variable should we give this? R. The radius. Okay? So when the radius is 4 feet, oops, we'll say when r equals 4 feet, we want to know, find the rate, so here we go, find the rate at which the area of the water is disturbed. What variable should I use? A. And I'm going to use capital letters for area and volume. You with me? For area and volume, we use capital letters. So A for area, B for volume. We do not know this, but we want to find it. Now the rates that are given in the and are unknown, check, done. Now we got to go back to geometry, and hopefully your geometry teacher forced you in a lot of ways to memorize all these equations that you're going to have to be very, very familiar with right now. Here we go. What is the equation pi r squared? Here we go. So the area is pi r squared. This is the equation that we're working with because we're not talking about circumference. We're talking about area of a circle. Now, this line is so, so important. This will make or break you as far as those of you who understand these two questions that you should ask yourself right here and right now. This will be very easy for you or will remain difficult for you. Okay, here we go. The two questions are this. Question number one is the variable changing or is the variable constant? Is the variable that you're looking at changing or constant? If it's changing, leave it as a variable. If it's constant, plug in that value immediately. Let me write that down. If it's changing, you're going to leave as the variable. If it's constant, we're going to substitute or plug in that value for the constant immediately because of constant multiple rule. You with me? Number two is, should we leave it as that variable? And 2 is the harder one, okay? Should we leave it as the variable or replace it with a different variable? We say in terms of what variable? Should we change, and that's a question that you're asking, to a different variable, the one that we're given? Okay, let me talk to these questions with you right now. Okay, here we go. What did I say A stood for? Area. Is the area changing if this was an active motion? Yes. So because it's changing, I'm going to leave it as A. Okay? The second question is, should we write it in terms of a different variable? Should I change A to something else, or should I leave it as A? I'm going to leave it as A because how else will I ever get this piece when I derive it? If I change it to a different letter, I will never be able to get dA dt. Okay, so that's question number 2. Go with me? Now let's check. We have to check all the variables with these same 2 questions. Does R change? Yes. So I'm going to leave it as what? R. Should I change R to something else? No, because how else will I ever be able to get a dr dt if I change it to a different letter when I derive these? Questions? All right. Why did I not highlight pi? Because it's a constant. Okay, here we go. So this step is done. Now we're going to differentiate right here, right now, in respect to t. What's the derivative of the left? dA dt. Careful, remember you said it, pi is a constant. So to me, I wouldn't even look at pi. I would just concentrate on r squared. And what's the derivative of r squared in respect to t? Yes, 2r dr dt. And now, yep, someone was about to say it, constant multiple rule back that pi into it. Okay? Now here we go. I'm going to use a positive 1 for dr dt. Remember, I'm looking for dA dt. That's my unknown. I'm looking for this. That means I should have an r somewhere. If not, I should be able to find an r. Because sometimes you're not just going to be given that r. You have to find it. What is r? 4. Oops, not there. So this will become pi times 2 times 4 times a positive 1 and dA dt. Guys, if you ever have something in pi, unless I give you a calculator, which I finally will give you a calculator for this test, there's some calculator pieces that you need the calculator for. If it's a non-calculator, just leave it in terms of pi. So the answer is 8 pi. Now, let's think about this. dA dt is 8 pi. Now, we got to think about our units. It's in respect to time, so we know it's going to be like feet per second or something like that. But because it's an area, because it's an area, you already said it, it's not going to just be a rectilinear foot. It will be a two-dimensional cross-section of feet squared. So this will be a feet, square feet, we'll say per second. Let's default to feet per second, okay? Unless it says, it did say. All right, feet squared per second. Let me tell you the difference. If it was volume, what would I have? Feet cubed per second. What if it was still area, but it was acceleration? It'd be feet squared per second squared. If it was volume and it was acceleration, it would be feet cubed per second squared. All right, good. Any questions before I move on to the first? Because that's just the first one. On a scale from 1 to 10, this is probably like a 2. Yes?
What if the rate at which it's increasing isn't constant?
If it's not constant, then you can't do that. Listen, did you hear what he said? He goes, what if the rate that it's increasing isn't constant? Then that's multivariable. That's more. That's like Calc 3. You won't experience any of that. Not this year. Okay? Here we go. Real quick, because I like Wilson's question. Real quick. The radius was increasing at a constant rate of 1 foot per second. That means dr dt is 1. What's the acceleration of dr dt? 0, because the derivative of this derivative, what's the derivative of a constant, which is what he was referring to? 0. That's important. Those are the level 7 to 9 problems he's already going to, that you'll have, that you're going to have to think about all these different things. Okay? All right, here we go. Water runs out of a conical tank. So real quick, let's come over here. This is two-dimensional velocity. Okay? And this is probably like a level 2. Okay, we're going to jump. This is like a level 4 to 5. Okay, this is a level 4 to 5. And this, let's read it and then you tell me if it's 2D. Actually, let's think about this. If I asked you what dH dt was, which is the rate of change of the height in respect to time, is it 1, 2, or 3 dimensional? Think about height. It's 1 dimensional. Okay? If I asked you to find this area and how it was changing as water was leaking out, so this area is changing as water is leaking out, is this 1, 2, or 3 dimensional? 2 dimensional. And then if I asked you the volume itself, that would be 3 dimensional. Okay? And that's a little bit of day 1 originally. That was interpretation of the derivative. I'm kind of tying it in as we do these problems at the same time as well. Okay, So this is, like I said, a level 4 to 5 depending on your strengths. Water runs out of a conical tank at a constant rate of 2 cubic feet per minute. Here we go. The diagram is done. Rates, we're about to give the rates that are given and the ones that we want to find. From this first sentence, does anyone know what I could write down just from this first sentence? Go ahead, Kevin. What? dV dt is negative 2 cubic feet per minute. Lexi, why did he say negative? It didn't say negative up here.
Because it's running out.
Because it runs out. So we have to, just from words, create all these small little subtleties when we build our equation pieces. Okay? So that's the one that has been given. Let's find the one that we need to find. What's the unknown? Or are there any other rates, not dimensions, not f of x's, but f primes? Are there any other rates that are given? No. So now, which one is it that we're trying to find? dH dt. We're trying to find how fast is the water level sinking. Look for all of these INGs will tell you the changing pieces, okay? Because that's a big focus of this unit. We're looking for all the things that are changing, okay? So we're looking for dH dt is equal to what when h is 4 feet. Okay. Let's move on to our equation. So far we have the diagram, we have the rates given and unknown. From what we see so far, put all these pieces together, relate them together. Matthew, what is the equation you think we're going to use?
So you're doing a volume of a cone.
Volume of a cone. So let me help you out. I'll help you memorize it right now. Look, it's a cylinder divided by 3. Yeah.
That's what I was trying to get the 3.
So it's a cylinder's volume divided by 3. So it's going to be 1/3 pi r squared h. Okay? 1/3 pi r squared h is the volume of a cone. Because a cylinder's volume is pi r squared times the height. And if I take a 1/3 of that, I will get the cone that fits into that cylinder. Okay? Here we go. Check. Now I got to ask myself those 2 questions. And I'm going to go through them one at a time. Let's see if you remember. Luke, what's the question that I asked first? Grant, what's the question that I asked first? Is it constant or is it changing? Guys, look at this problem. Is the volume changing or constant? It's changing. So I'm going to do what? Keep it as the volume. Keep it as V. Keep it as a variable right now. Okay? Am I going to use a dV dt anywhere in this problem? Yes, I am. I'm going to use dV dt. So I'm not going to change it to a different variable. I need to leave it specifically as V. So let me go through those questions one more time. Question 1, is it constant or changing? It's changing, so leave it as a variable. Question 2, should I leave it as V or change it to a different variable? Well, I need V. How else will I ever get dV dt when I derive? So question 2's answer is I leave it as volume. Okay? Let's go to the radius. Is the radius constant or is it changing? It is changing because I'm talking about the water. I'm talking about the water. The radius, when it's full, is here. Okay? The radius right here, it's obviously changing. So I'm going to leave it as a variable. Should I leave it as R or should I change it to a different variable? I'm going to change it. I'm going to change R to a different variable in terms of a different variable, and I'm going to change it to the variable that we are using. Nowhere did did it tell us what dr dt is? Nowhere did it ask us what is dr dt going to be. It's not even talking about the radius. What does it talk about? The height. So we want to change. This is huge. This will separate the easy from the difficult problems. We want to change it to the variable that we're working with. Okay? But nonetheless, it's still a variable because it's changing. Okay, is h changing or is it constant? It's changing. Leave it as a variable. Should I leave it as h or should I change it to a different variable? I'm going to leave it as h because how else am I ever going to get this piece when I go to derive? Okay? Alright, so let's go ahead. I just realized just now I didn't fully finish step 1. I need to diagram this a little bit better. The radius of the top of the tank is 5 feet. So this right here is 5 feet. And the height of the tank, notice I'm talking about the tank, not the water. I'm talking about the original construction of the tank. Yes?
Do you only change the variable if it doesn't add the full derivative of that variable?
Yes.
So you just change it to in terms of something it's already asking for?
Perfect. Yep. So this will be 10 feet. You with me? How fast is the water level sinking when the water is 4 feet deep? So what I'm going to do is I'm going to change r to h. This is how I'm going to do it. The radius is to the height as 5 is to 10. Proportions. Geometry. Geometry proportions. The radius is to the height, the relationship, as 5 is to 10. You with me? So if I now saw, and I'm trying to change it to h. So if I'm trying to change it to h, that means I'm trying to get r by itself in terms of h. So I'll have r over h is 1/2. Otherwise, r is 1/2 of h. And some of you will put h over 2. So guys, if r is h over 2, I'm going to substitute that right here. Because now I have this in the form of all the variables that I will use, or the ones that I'm trying to look for. There aren't any r's anymore. Because I'm not looking for dr dt, nor am I given dr dt. Can someone tell me why can I do this with the tank? And there he goes. Because the tank is a constant. That constant proportion will always exist even as this is emptying. The radius to the height will always be at a proportion of 1/2. So don't do it to the water, do it to the original tank. Because you'll see these for sure. Alright, now we're ready to do the derivative. Okay? And what I would suggest to you always before doing the derivative, whatever I told you since the beginning of the year, always do what before you derive? Always simplify before you derive. So if I look at this, the way I would look at changing it would be put my constants together. You get h squared over 4. A lot of people would miss that 4. And I would even simplify that even more. You see what I did just now? I just squared the h and squared the 2 to get h squared over 4. And what I would do, let me make some room over here. Come on. I'm going to simplify this to h cubed. And then what? What's my constant? Pi over 12. So how I piece the 3 and the 4 together? And now constant multiple plays a big piece into this. Don't even look at pi over 12. What's the derivative Yes, Gabe.
What happened to h being divided as well?
Well, h is in the numerator, and they multiply. So you just add their powers to get h cubed.
Yeah, but it was over 4, so it'd be h cubed over 4, right? And then
Yeah,
multiply
true.
3, so
H cubed over 4. This 4, I just grouped it with this 3, and I pulled it out as a 12.
Well, why wouldn't it be pi h cubed over 12?
It is. This is the
No,
same, guys.
being divided.
This is the same as pi h cubed over 12. Those are the same. I just constant multiple ruled out the constant just so I can just see I'm just deriving h cubed. Cool? All right, here we go. What is the derivative of h cubed? 3h squared dh dt. Then multiply back in your constant, and you tell me what's on the left side. What should I write on the left side? No. dv dt, right? dv dt. Yeah, we're going to substitute and solve here in just a bit. So now, let's plug in all of our, let's do substitution. Let's substitute -2 here. I always try to simplify as much as I can, as early as I can. So what am I going to simplify this to? Pi over 4. What am I going to plug in for h? 4. And get this, you only have one unknown. Guys, you should only always have one unknown that you're looking for. If you have more than one unknown, then you did something wrong, or you got to do a little bit more to get that piece that you're still missing. That's why there's no one way to do all this. Here we go. I see 16 that will reduce with 4 to get what? 4 pi. And a lot of these are without calculator. So that my final answer, dh dt, is -2 or 1/2, right? Because -2 divided by 4 is -1 over 2 pi. Now let's think about this. We've got to do units. h, 1, 2, or 3-dimensional? 1. So it's not going to be feet squared. It's not going to be feet cubed. It's just going to be feet. Is it over seconds or seconds squared? Oh, it's minutes, yeah. Is it minutes or minutes squared? Minutes. Why is it minutes and not minutes squared? Because it's velocity, not acceleration. So this is, to me, I think this is more of a level 4. But it's okay because you'll just get more practice with it. There's a lot going on, right? So please ask me if you have questions right now before we go, because we have other ones that are coming. Okay, exposure, and practice. Because I promise, a lot of people say this, when you're doing it, Mr. Gomez, it makes sense. But when you go to do it on your own, this is one of those, that's why I'm begging for questions. So that when you go on your own, it's not like crazy foreign. All right, here we go. We got to change some things on this thing, because I copied and pasted this from your ebook. So a fish is reeled in at a rate of 2 feet per second from a bridge. So pretend that boat is a fish, okay? It's a big fish.
Why'd you make it a fit?
Done. All right. So a boat is reeled in. That's awesome. At a rate of 2 feet per second from a bridge 16 feet above the water. At what rate is the angle between the line and the water changing when there are 20 feet of line out? Yeah. Go to dreads. Immediately, let's draw our pieces. Okay? And what I see here is pretty much, this is the most important thing that I should be looking at. Okay? And of course we know that it is a right angle right here. Because it won't tell you, hey guys, use a right triangle and stuff. No, you have to come up with all this from the experience and practice. Here we go. If I looked at this, let's give it some variables. What could I give these variables? I could give it x, y, and z. This is what I want you to do with triangles. X is horizontal, y is vertical, z is the diagonal. Please do that for the sake of consistency. Don't use A, B, and C, even though I know that's the Pythagorean theorem. Please use X, Y, and Z. All right. Do we know anything that, what else can we add to this picture from the reading? Y is 16, right? So let's do that. Y is 16 feet. And Z is 20 feet. Okay? I think I heard it. But it's okay if you didn't see it yet. I'll show you in a minute. The diagram is done. Rates that are given or unknown. I'm going to throw you right into it, guys. What rate, Drew, are we given? 2 feet per second. Is it a positive or a negative? So if it's reeled in, Z is decreasing. That's huge, because otherwise one negative, you missed a lot of points that it goes through, okay? And I will not sit there and see, would they have gotten this right if it was a positive? I'm not going to create 2 keys, so please make sure that you understand the level of those negative mistakes have to refine big time in this unit. So negative 2 feet per second is what? Drew? Go for it, Matthew. What is it? dz dt. The rate of change of my hypotenuse in respect to time is a negative 2 feet per second.
So we can basically make anything.
Yes.
Yeah,
Yes.
okay.
Yeah.
Okay.
So there's a lot already of, oh, okay. That's what we're doing. Grant. We're still doing rates. What rate are we looking for?
The rate of change of the angle.
Okay.
So like d theta.
So it'll be d theta over dt is equal to something when what, Grant? When z is equal to 20 feet. Already, this is different. Again, we're going to have to think of everything that we've been taught. So what we're looking for, in case you haven't already figured it out, we're looking for this. And we're not looking for the angle, we're looking for the rate of change of that angle. At the exact moment, picture in time, when z is 20 feet out. Are we good? Okay, here we go. What equation, Matthew, should we use? From all the pieces, listen, ask yourself this question. Relate all your pieces together. Sine is what we should use. Because if you choose the wrong equation to use, you can make it very difficult. And it'll be longer to get your answer. Sine is what we're going to use. Okay? So here we go. The sine of theta is equal to what variables? Y over z. Here we go. The most important 2 questions. Question number 1. Is theta changing or constant? It's changing. So I should leave it as a variable. Question 2. Should I change theta to something else? No, because how else will we ever be able to get d theta dt piece? Let's use y. Is y changing or constant? Constant. Because it's constant, we're going to plug in right now, before deriving, we're going to plug in what? 16. Is z changing? Yes. So I should leave it as a variable. Should I leave it as z or change it to something else? I'm going to leave it as z because how else would I ever be able to use this piece that they were giving me? Raise your hand, honestly, if you understand the two questions. Okay, those are the most important questions, okay? This will make it easy. Here we go. Let's take the derivative in respect to time of exactly what we see implicitly right now.
Real quick, if it's changing and it gives us a value, can we leave it?
If it's changing and it gives us a value, we leave it as a variable. Very important. If it is changing and they give us a value, don't put it in until we're ready to use it. But still, if it's changing, leave it as a variable. Did you hear that question? All right, the other thing is this. Y'all were asking me earlier, is it implicit or explicit? Look at this. This is explicit, even though it's still something dt. But I was looking for dv, or actually, it was explicitly given to me as the volume. But I wasn't looking for the volume. I was trying to look for dh dt. You with me? This one is implicitly given to me because there's not a variable all by itself. But it doesn't matter. Implicit or explicit, my goal is to substitute and solve at the end. Okay? All right, Evelyn, what's the derivative of the left side? Cosine theta times,
Would it be the derivative of theta over
yep, d theta dt. Is equal to, now look, I have 16 over z. I'm telling you, to be honest, how many of you would do quotient rule? It's a little bit too much work if you try to do quotient rule, okay? Looking at this, I'm going to bring this up as a rewrite because of two things. The top numerator, what? Is one term, and it's a constant. So now the derivative, Madeline, of this is going to be what?
negative 16 d
To the negative 2, keep going.
dz over dt.
dz dt. Guys, I'm going to move it right now. This z to the negative 2, I'm going to move it downstairs. And just like Madeline said, I still have to remember my dz dt. Okay? Alright, here we go. We're going to plug in dz dt with a negative 2. We're going to plug in z with 20. We're doing substitute right now. I'm looking for d theta dt. That's my unknown. But I still have a variable right here. I still have cosine of theta. So what should I do? Okay, arc cosine of whatever the side is. Do you see how right now in this triangle, guys, I have 16, 20, theta. What I could do is say the arc sine, you with me? Look, this is the hard way. The arc sine of opposite over hypotenuse. This will give me theta. Raise your hand if you agree. Yeah, this will give you theta. And then take the cosine of that. That's the hard way. I think the faster, easier way would be this. 2016 is like a 3, 4, 5 right triangle. So it's 12. Because all of these are by a factor of 4. So it would be a 3, 4, 5 right triangle. You see how we did that? And all I cared ever, this is the one that it's easy, but you can make it hard. This could be a level 7 because depending on what you know and how you try to work this out. Instead of doing this and then taking the cosine of that, no one has time for that. Just solve the triangle and ask yourself, what is the cosine from this angle? 12 over 20, which is the same as 3 over 5. So 3 over 5 times d theta over dt is equal to, let's plug this all in, negative 16 over 20 squared times negative 2. And this would be without a calculator. So I get a positive 32 over 400. And what am I going to multiply both sides by? 5/3. That cancels that to a form of 1. And what do I always do before multiplying straight across? Simplify. 5 over 400 is what? 1 over 80? 1 over 80? Does anything else simplify? You can simplify more. 32 over 80 can simplify, like they both have a what? An 8. So this is 4 and 10, and you could still keep going. You see what I'm doing? That's easier. I'm telling you, for the speed that you're going to have to do these problems in, 4 over 10 can reduce to what? 2 over 5. So now I'm left with 2. Whoops. 2, 1, and come on. 3 and 5. So that the answer is what? 2 over 15. d theta over dt is 2 over 15 what? Here's the thing. Radians per what? What's the time? Seconds? Because calculus is so radical, we're always in radian form. Okay? We're never ever in degrees. Physics is, but calculus is not. Make sure when you take your physics, raise your hand if you're taking physics C. Guys, there's been people that scored 3s instead of 5s, or even 4s instead of 5s, because they were in the wrong mode on the calculator. Physics is in degrees, calculus is in radians. Okay? Any questions before we keep going? Again, this was like a level, in my opinion, like a level 7. Because there's a lot of easy stuff that could go wrong. Okay? Is it 1, 2, or 3-dimensional? The angle, the way it's changing, it's not 2. It's not an area. It's like a rectilinear angle, but it's at a like an arc. Okay. All right. Yes, we have a lot of practice, guys. These get difficult. Okay. Now we have to practice. We have to. No, these are real world application. There's a lot going on, and there's so many. What I'm trying to do is expose you to, when I say here's your problem, you have enough experience to build your own solution. The less of these you do, I promise, the more it's going to hurt to understand. Ironically, the more you do, it'll hurt, but you will understand. Okay. So a man 6 feet tall walks at a rate. So let's say that, yeah, this is weird, but let's, oh man. So let's pretend like he's walking this way, guys. I'm not going to try to fix that, but he's walking this way. So turn his body and walk that other way. All right. He's moonwalking. There we go. Moonwalks. There you go. I love that. Who said that? Bonus points. All right, here we go. a man 6 feet tall, so 6 feet, moonwalks, that's awesome, at a rate of 5 feet per second toward a light pole. And the light pole is 16 feet tall. That means his velocity, well, we'll get to that. Hold on, just a minute, hold on. So at what rate is the tip of the shadow moving when he is 10 feet from the base of the light? At what rate is the length of the shadow moving when he is at 10 feet from the base of the height? So listen, this is a little bit difficult to see. So here's his shadow. Because it's a light, right here, here's the light, it's emitting, it creates this shadow on the ground. Now, the tip is just referring to, at the tip of his shadow, how fast is that moving? Whereas the length is talking about the entire length. How fast is that moving? You with me? So think of the tip of the shadow like one point that is moving. But think of the length of the shadow as a line that is getting smaller. Can you tell me why this line is getting smaller? Because I'm going to the light, and the light is going to emit a smaller shadow. And see, you have to develop this from a problem, from all this experience, because there's a lot of different types of problems you can create. Yes?
Are we measuring like the rate at which his shadow gets smaller, or?
Well, let's do that together. Well, I'm not there yet. I was just trying to understand, make sure that you understood a point versus the line interpretation. I'm trying to make you, I'm trying to help you this right now. We're still doing that. Okay? Now let's go to the rates, okay? But are we understanding, guys? Do we understand the picture? All right. Here we go. The rates. What rate is given? 5 feet. Should it be positive or negative? Negative. Now here's the difficult part. What do we label it? dx over dt? All right, here we go. No worries. I don't expect you to, because this is a difficult problem. And when I first looked at this years ago, this is actually a similar right triangle kind of problem with proportions. And it's hard to see that. But what it really is doing, and I want you to write this in your notes, it's this picture right here. And what I want you to do is I want you to label this X. I want you to label this, I know it's counterintuitive, Y. I want you to do this as height and this as Z. Okay? So the distance that he is away from the base is X. Go with me? Okay, here we go. We need to set up, so if we're asking for part A, at what rate is the tip of the shadow moving? First of all, we can finally put this, what this is equal to. There you go. dx over dt. You understand? If you don't, you have to stop me right whenever it happens.
Is it because he's already passed Y?
So y is the measure of that length. You're never past y. There's always a y in between your feet and the tip of the shadow. And there's always an x per se, unless you're right on the flagpole, between you and the light pole. Okay? All right, so part A says at what rate is the tip of the shadow the tip of the shadow will be d something dt when what? Come on, guys. X equals 10 feet. This is for the tip of the shadow. The length of the shadow is something else. It's d something dt when x is 10. Here's what we do. Which one of these, be honest, some of you are really thinking about this to far level already. Which one is easier to name right now? As far as d something dt, the tip of the shadow or the length of the shadow? The length. What is it? dy dt. Don't overcomplicate the tip of the shadow. What is this? And then the biggest reason is this.
X, Y.
Nice. X plus y. X plus y is that one. Now let me tell you why. It's in reference to the light. I need to talk about from the light pole to get the tip of the shadow, I need the x and the y. Because if I'm just talking about the length, I know the light's related to it, but I'm talking about from my feet to the tip of that shadow. That's the length. You with me? So I don't need x plus y for the length. It's just from my feet to the tip of the shadow. We good? All right. So this one, I'd say is a level 7 or 8. Okay? Just because when and where you use this can be a little bit confusing. And the diagram alone was hard to come up with. All right. E, the equation. From all the pieces that were given, remember, I didn't draw them over here, but I'll do it now. 16 and 6. From all the pieces that were given, what do you think is a good equation that we could create from this? Don't be afraid, try it. Kevin, what would it be? No idea. Grant.
Square root of z squared minus h squared equals x plus y.
Okay, so he's going straight for Pythagorean theorem. Do you hear what he's saying? He's going. What? It's not. Hey, that's a good attempt though. I mean, that should be your first go-to. When you see a right triangle, go straight to Pythagorean theorem. Okay, but it's not on this one. Okay, this is why it's at level 7, because a lot of people don't think of it. It's a proportion. So 6 over y, or you could put y over 6. The height to the base is proportional to the height, you with me? To the base. Now, can someone tell me, why did I put 16 instead of h? Because it's constant. That, plug it in now. Because that I keep saying flagpole, that light post will not change. Okay? Why is it 6? Because hopefully that person's height doesn't change as they moonwalk. Okay? That'd be cool. Alright. Yeah. Alright, so from here we go. You're going to get 6x plus y is equal to 16y. Which you could simplify to 6x plus 6y is equal to 16y. All I'm doing is basic algebra right now. Which you can simplify to 6x is equal to 10y. Guys, believe it or not, your equation is that right there. Okay? Which is weird. But this is the proportion that x is related with y. So here we go. Does x change? Does x change? What we said was x. Does it change as he moonwalks? Yes. So leave it as x. They both change. So we're going to leave them as their variables right now. Okay? Here we go. Should I change x to y? No, because how else are you going to use this piece? Okay, here we go. The derivative of the left is 6 dx dt. The derivative of the right is 10 dy dt because of constant multiple rule. You with me? Dx dt is negative 5. So therefore, dy dt is what? Negative 3. So here we go. Dy dt, which is the length of the shadow, part B, is a negative 3, what? Feet per second. Is it seconds squared? No, because it's not acceleration. Is it feet squared? Whoops. No, because it's not area. So how do we get this? You just add them together. Guys, this right here is dx dt plus dy dt. So we're going to plug, we just found dy dt, and if we plug it in here, negative 3, and we're going to add it with dx dt, we get negative 8. D of x plus y over dt, otherwise the rate of change of the tip of the shadow is moving negative 8 feet per second. Listen carefully. On the test, you also have free response questions to where I want you to describe it in words. So if I said, at what rate, in a sentence form, at what rate is the shadow moving? This is very important. Moving and changing are different. Changing is like velocity. Moving, who said that? Is like speed. Because speed is the absolute value of velocity. So in other words, the speed limit on the highway says this. So I've thought about that too. Well, what if I don't go 80 and I went negative 100? Could they give me a ticket? Well, yeah, they could, because they're saying the speed limit. They're not saying the velocity limit. But anyway. That'd be cool. All right, velocity is changing, speed is moving. So with this one right here, whoops, you're going to say that the rate of change of the shadow for part B is moving at a rate of 3 feet per second. Okay? This one is moving at a rate of 8 feet per second. But it's changing at a rate of what? Negative 8. You with me? It's changing, let me finish this up, at a rate of negative 3. What if I had, let's say, a radius that was decreasing at negative 3 inches per second? I would say this. It is decreasing at 3 feet per second. Because if I said it's decreasing at negative 3, I'm actually doing a double negative, and I'm saying that it's increasing. So now you know, moving versus changing versus decreasing or increasing. Know how to use them when and where in sentence form. Okay? If you have a question on that, I can answer it right now.
I was gonna ask, like, when the person is moving towards the light pole, you say is moving at, like, whatever it was towards light pole, would that be
Okay, so let's say that this person is here and you're moving toward this. What is it that you're talking about? Are you talking about the rate of this? Okay, so you're going to say, let's say that this rate is negative 5 feet per second. See, this is easy when I ask you to do it in this form. But when I tell you to do it in sentence, then that's when the questions come in. You could say that it's moving at what? 5 feet per second toward the pole. You could say that it's changing what? At a negative 5 feet per second toward the pole. Because the changing is constituting that magnitude. Is it a positive or a negative direction that this thing is changing? Go with me? And the decreasing, you would say it's decreasing. You could say, I see what level you guys are asking now. So, if you're decreasing, you would say that the rate of change, since it's already negative, is decreasing at a positive. Okay? You won't have questions to that level. You won't. Nowhere near that level. That's cool stuff, though. Any other questions that you guys have? Just don't do double negatives on the sentence interpretation.
How much did you count off for missing?
1,000,000 points. Oh, negative mistakes can be, no, this is a really good question. Negative mistakes, if they're at the end, are 1 point. If they're at the beginning, if it's a big problem, it could be 8 to 10 points. So you don't want to make negative mistakes. But the attempt is still 1 if you at least attempt.
Not after the first semester.
Not after the first semester.